So we're going to handle the unstructured mesh presentation a little bit differently, and we'll see how successful it is. We decided to attempt to give you one integrated presentation with multiple presenters. We're going to hop up and down at various times during the presentation. So first, let me introduce the FASTMath Unstructured Meshing team, but you can see that involves investigators from Argonne National Labs, Lawrence Livermore Labs, Sandia National Labs, RPI, and the University of Colorado. In terms of what we're going to cover in today's presentation, I'm going to comment about unstructured meshing techniques, their advantages and disadvantages, and then we will talk about the two core infrastructures that we have been developing today. Vijay will talk about the one, I'll talk about the other. So the advantage of unstructured meshes, as already mentioned, is that they can easily deal with arbitrary geometries. That is, we have the ability, and do it on a regular basis, to go automatically from CAD models to meshes and analyses of them, and adaptive meshes, as you'll see in examples. They easily fit to geometric features. They can be graded. They can account for anisotropy in the construction of the mesh in a variety of ways. So given a CAD model, we can do entire simulations in an automated sense, which, if you're thinking about the entire workflow, if you're able to do on your massively parallel computer, you're solving in 30 minutes, but it took you 3 weeks to generate the mesh, are you that much ahead? So we tend to focus on methods that can be automated and be used with adaptive techniques. But as we'll see when we list the disadvantages, there's a cost associated with that. Costs associated with that are more complex programming structure, methods needed, particularly when you deal with them in parallel. In addition, you do have to exercise care because the quality of the mesh does influence the results in a variety of ways. It could be as simple as element shapes that influence the accuracy because you have a very sensitive discretization technique, or even with less sensitive discretization techniques, you may have conditioning problems introduced. So you do have to be fairly careful, although combinations of a priori and a posteriori methods are available for dealing with this. So the goal of the FASTMath Unstructured Meshing team, to a great extent, is to provide tools that allow developers that wish to use unstructured meshing techniques the ability to avoid some of the pitfalls and be able to address them with these tools. And that will be providing component-based tools that can be integrated with analysis codes at really multiple levels through APIs. They can be low-level APIs that deal with mesh entities at one at a time, or at a slightly higher level, which I'll mention for an example later on, of in-memory integration of adaptive techniques into an analysis code. In addition, we do work on providing, on addressing specific technical gaps, and you'll see a couple of specific ones there. But for example, Vijay will talk about mesh-to-mesh solution transfer technologies that are needed for when you're doing various multi-physics problems. You need tools for that, and there are really not that many available, so we need to develop some there. I'll mention just very briefly dealing with meshes that are higher order in terms of the geometry of the mesh, because if your mesh, geometric approximation, your mesh doesn't go up in order as you go up with higher order methods, you're solving the wrong problem. And we do work very closely with DOE applications, as indicated on this slide. Some of the applications, both DOE and a couple from outside of DOE, where we're bringing the FASTMath unstructured mesh technologies to bear. Our parallel mesh infrastructures focus on providing certain base functionalities, that is, dealing with the mesh. In our case, we deal with them as partition meshes, consistent with how the methodologies used today, and consistent with message passing, although we also then do additional things with that, as you'll see. We mentioned some architecture-aware work. And then the functionalities to manipulate that partition, to deal with copies, the halo meshes or ghost types of meshes, and associating data with that, such as fields. In addition, key services, then we'll emphasize in the discussions load balancing, in particular dynamic load balancing that can be used as you're changing the mesh as it goes, mesh-to-mesh solution transfer, the optimization of the mesh in terms of element quality as well as its general adaptation. And the two infrastructure that will be presented are Sigma and PUMI. Right, so just a little background on the basic concepts of partition mesh. The idea is on process you can deal with a mesh in a serial sense, and that the partition, there's a partition model, if you will, and those are boundaries to this mesh that are going to deal with the parallel communication information that is needed for that. Now you need the ability to change these partitions on the fly as needed by the applications, either due to the mesh changing or just due to the fact that load balance may change in a multi-physics problem. The idea of ghost copies for saving space, you want to, every mesh entity is owned by one part, is on one of those parts, but it may be copied on others, and we have general capabilities for being able to define how you do that, because different applications have different requirements for that, and we're relying on our ability to use mesh topology, the hierarchy of mesh entities, from regions to faces to edges to vertices, to give us very flexible control of that. In terms of the base tools, because we had to create the mesh, you want mesh generation techniques, must be able to create mesh over complex domains. We are already doing meshes approaching 100 billion elements that have been developed, that's mentioned earlier. We want high levels of automation to avoid meshing bottlenecks with this. The mesh adaptation must be able to use a posteriori information from a variety of sources to then improve the mesh in very general ways. Must account for the domain in that process, not just adapt the mesh against the mesh geometry, but against the actual domain. And you want the ability to do that with anisotropic meshes that meet the requirements of analyses, such as boundary layers for highly anisotropic problem areas. Mesh shape optimization, very important for controlling element shapes, is needed by various discretization technologies, as well as to help control the number of iterations for solvers. And we want all these functions to operate in parallel on large meshes and integrated very seamlessly as possible with application components that do the analyses. Fields and solution transfer, obviously the purpose of the mesh is to be used in the solution of some problem. So there are going to be these fields defined on it. They're going to be tensors defined over the mesh quantities. We need to deal with those and their transformations in an appropriate sense. We want to provide functionalities for iterating on them, integrating them, differentiating them, and supporting operations such as transfer from one mesh to another, meeting constraints such as conservation, et cetera. At this point, I'd like to let Vijay take over and describe the Sigma capabilities.
So I'm going to talk about the second tool that Mark discussed. So I call it Sigma. To clear up Laurie's confusion, we renamed this pretty recently. And Sigma stands for Scalable Interfaces for Geometry and Mesh-Based Applications. So we've been talking about MOAB quite a bit, but Sigma contains a couple of other components in there. So one is CGM, which is the Common Geometry Module. It has the API and functionality to actually expose the actual geometry model underlying that you're trying to model. So we have several different format supports. So one is the open source OCC model, and we also have support for the ACES model that's used inside Qubit quite a bit. And MOAB is the mesh-oriented array database, and this is the actual unstructured mesh data structure that's able to understand the mesh in parallel and define the entities and provide the API to traverse through the different entities. So it provides a scalable mesh data structure to actually create your own application and uses efficient array-based data structures. We also have parallel I/O implementation in various different formats. So the prime native format is HDF-based. And we can also do in situ visualization with this particular HDF format with ParaView. So we can actually create plugins and look at the solution as you're solving the problem. So Mark also mentioned about different mesh generation algorithms. So MeshKit is a library, a component tool, which actually contains various different algorithms, also interfaces to several different existing external mesh generation packages too. So one of the primary interfaces is with Qubit. So you can actually define your geometry model with CGM and give it to MeshKit to actually interface with Qubit and generate the actual mesh that's needed for the applications. So some of the other things that we're also working on is Coupe, which stands for the Couple Physics Environment. So we use this in some of our nuclear engineering applications to couple various different physics together in sort of, well, so there's quite a bit of work being done on this scalable solution transfer. And I'll talk about that in some of the later slides. And Coupe so basically sits on top of various different physics components and drives the solution process. And one of the important processes that happens underneath is when you're solving mesh-based applications, you need to transfer the solution from one physics, which has a very different resolution, to the other physics that might have pretty coarse or pretty fine-grained resolution itself that's dictated by the physics. And we also need to apply conservation and normalization after you do the solution transfer. So that becomes pretty important. We have also created some interfaces to solvers. So Barry mentioned about the DM interface. So we created a specific implementation that sits on top of MOAB as a native data structure and lets you create your own discretization. And it brings in the scalability of both the solvers and the mesh package together. So the next few slides, I'm going to concentrate more on solution transfer and the algorithms that we have in MOAB specifically. So this is about the point location. So when you're trying to do a mesh transfer, solution transfer problem, one of the most primary things that you need to figure out is how are you going to locate some points that you care about from a source mesh onto a target mesh. We are assuming that the domain, the geometry domain is still the same between two different physics. So from the source mesh, the physics, maybe it's using a different quadrature points to actually assemble the system of equations. So you could query based on the quadrature points or the actual vertex entities from the source mesh and find out which particular element it belongs to on the target mesh. So this involves a geometry search. So we do support parallel point and element query functionality inside MOAB. So this is provided by a very specific tool. It's called MB Coupler inside MOAB. We're also trying to make the coupler technology more flexible in order to support various different discretization strategies. So right now we support first and second order Lagrange elements, Lagrange basis, and pretty high order spectral basis. And we have different applications using them in several finite element and finite volume discretizations. So as I mentioned, so this is more about Coupe. So Coupe sits on top of several different physics and uses MOAB internally, uses PETSI as its underlying solver to drive the whole process. And these are some application, well, solution profiles from some particular problems that we ran in nuclear engineering problems. So more about the algorithm itself. There are typically 4 to 5 different stages in order to do the solution transfer from one physics to the other. So first is the initialization phase, where you have your source mesh. So the green represents the source mesh, and the red is your target mesh, where I want to locate your points. So on the source mesh, you could decide what particular points that you care about, where you want the solution from the other couple physics to be evaluated so that you can assemble your couple discrete operator in memory. So in order to compute the actual solution itself, the source mesh points are actually located on the target mesh. And so we actually create a bounding box hierarchy in order to initialize sort of discretization of the points itself and build a KD tree based on that. So the bounding boxes are still sort of coarse. So a certain bounding box could actually, well, it depends on the resolution of the actual meshes itself, but we actually construct a KD tree based on the bounding boxes and use that to actually perform the point location once the query is performed. So this is the actual setup phase, and to perform the interpolation, we use the point query information and then use the data that's aggregated to perform the actual interpolation. And this is where the discretization kernels come in. And once we perform the interpolation, the data is transferred back to the source partitions that actually originally requested the particular data. So this particular aggregation is written in such a way that the actual data transferred is minimized using a crystal router algorithm. So once we actually compute the interpolation, we can also apply. Once we compute the interpolation, we can also apply several normalization techniques so that certain quantities are preserved when projected from the source mesh to the target mesh. So this it shows some of our scalability results with the solution transfer process that I talked about before. So this was on BlueGeneQ at Argonne, Mira. So we demonstrated about 70% scalability with about 500,000 cores. So we actually varied the points per rank. The average optimal value for applications are typically around 10,000 points per core, and so we varied the range of points by quite a bit and measured both the L2 error in the solution transfer, and this shows the efficiency, or actually the scaling of the projection. So this is on a cube, 1024 by 1024 hex cube. The solution is transferred from an original tet mesh to a hex mesh, and we measure the scalability for performing that operation. So this is the breakdown of the different operation that I showed before. The yellow represents the actual point location process itself, while the reds here are the actual setup cost. So you can see that the setup cost dominates quite a bit and doesn't quite scale as well. But the advantage, or sort of the pros here, is that the setup is typically done. So if you're using static meshes on two different physics, so you know what's your source mesh and a target mesh, you can actually perform the setup once, and so that kind of gets aggregated. Well, actually, that the point location and the interpolation is what takes the most time. So this happens only once during the whole simulation. So it kind of gets buried in your actual process, because you're going to do the solution transfer over and over when solving your time-dependent problem at every nonlinear step. So the interpolation is what matters. But of course, we are actually trying to remove the bottleneck by changing the tree structures. So we're considering bounding volume hierarchies and bounding interval hierarchies to actually better time complexity. So this is another different application where we use the solution remapping with conservative transfer. So this is a climate application. So this basically solves a tracer transport problem, where the actual solution resides on an arbitrary Lagrangian Eulerian formulation, and so as the mesh moves during the time step, we actually do dynamic repartitioning to minimize the actual data transfer. And the advected solution for the tracer transport is also remapped during this process. And we have had good success doing this too. So this was in collaboration with several other institutes.
So I'm going to pick up and talk about the second parallel mesh infrastructure, which we refer to as PUMI for parallel unstructured mesh infrastructure. It employs a complete representation that allows us to get any adjacency in order 1 so we can support whatever any application would want. Everything's controlled through the partition model for the parallel operations. But our development of this, as Laurie mentioned, was focused on being able to support evolving meshes that are adaptively changing. We have coupled it very closely with very robust, fully automatic mesh generation technologies from CAD systems, can do dynamic load balancing, and has been mentioned, it has been used in conjunction with the dynamic load balancing tools to be able to take meshes up to 92 billion elements on 750,000 cores. We are also doing architecture-aware work with respect to this. There's been discussions throughout the week of being able to use accelerate, well, first being able to use large node count systems that have a lot of cores per node, requiring hybrid types of methods, and then the use of accelerators. Our goal is to, of course, address those areas, and our desire is to do that in a manner that keeps it as hidden from the application as potentially possible. So, for example, with the hybrid, one does not have to know that at one level it's using threading, at the other level it's using MPI. There's just a partition model. The fact that it's at 2 levels of hierarchy, the application does not have to account for, although if it does account for it, it can get some advantages. Referring to mesh generation, we're using some tools that happen to be from Symmetrics that can take any combination of CAD models and triangulations. It could be voxel data from images. They can create very well-controlled graded meshes and do this all in parallel. For example, 1 billion element meshes generated in 8 minutes on 256 cores. I think the example that's going to be done is a 13 million element mesh, but they've done 13 billion element meshes on 2048 cores. The mesh adaptation procedures are fully parallel. The specific strategy selected for this is to have a generalized set of mesh modification operations that can be applied in any combination to give you the same effect as total remeshing without doing remeshing. It has advantage of being able to support anisotropic meshes, dealing with the geometric domain complexities of either the evolving geometries or just adapting to the geometry, allows you to get whatever accuracy you want. And because we're doing it with mesh modifications, we can also do solution transfer on the fly with very localized operations, and also to satisfy constraints more easily, because if I just do a local refinement, I don't have any problem satisfying conservation. This slide just indicates some aspects of that, which I'm not going to explain, other than to indicate it does work always against the actual geometry, whatever that definition is. But for example, a CAD model, it is fully parallelized, and it supports also curved finite element types that I'll touch on at the very end. Also in PUMI, we have a fields infrastructure that is an array-based infrastructure for supporting fields and the tensors on that, and supports the various base operations on the mesh. Recent developments being done on it, supporting, for example, a fusion code going from a 2D to 3D automatically as part of the run, history-dependent solution transfer. With that, the local solution transfer, the idea there is if I'm carrying out an operation that's local, why don't I at that same time deal with the change of the solution field, whether it be a refinement, a collapse, or swap. The status is, as mentioned, we've done very large meshes. It supports the local solution transfer. These are just some pictures of a couple of different fluid dynamics applications, one blood flow, the other is an aerodynamics application. I show these pictures because it shows the ability to do anisotropic adaptation, including hybrid types of meshes with very large aspect ratios, 10,000 to 1 aspect ratios in the boundary layer, maintaining that while adapting the boundary layer. We also deal with evolving geometry problems coupled with particle methods for adaptation driven by multiple needs. I've already mentioned the work being done with the fusion application. Lori had mentioned the other fusion application we're involved with where we provided meshing tools. I guess the one comment I wanted to make on this is that we did introduce a 60-fold improvement in their meshing time. However, I have to readily admit we had to do almost nothing other than spend about 6 months talking back and forth to find out what their really meshing requirements was. And then it was very easy for, in fact, Fan Zhang, who is one of the students in the courses this year, to put together a set of meshing tools to be able to generate this mesh. And the actual runtime for the mesh is about 1 minute. About the setup time is in total accounts for about 10 minutes. Work we've done on the linear accelerators. Lori did mention this. I'll just mention the most recent work in that we have gone from being able to not only do quadratic geometry meshes, but up to now up 4th order G1 meshes that are not only continuous in value, but continuous in first derivatives between elements in a G1 sense, which means you cheat at the vertices a little bit. And this can be even taken to higher order than that.
And does anyone have a question about meshing?
Yes. Do you generate, just trying to make sure that I understand correctly, so the meshes are generated in parallel?
We can generate the parallel. Well, we don't actually, in FastMath, we're not writing mesh generators because there's a lot of work out there. Vijay mentioned MeshKit, which is integrated into it a number of existing meshing tools, as well as added specific meshing tools as they needed, primarily, I believe, for nuclear applications in that. With PUMI, we've integrated with a number of different meshing sources, but we most heavily use the mesh generation tools from Symmetrics, which happens to be a software house.
But that means you've actually divided into blocks and then different.
No. You have a CAD model, you press the button, you get a mesh. You don't have to do any work to make a mesh. You give me a CAD model,
Right, but when you generate that mesh, you're generating your distributed.
Okay. How parallel mesh generation done is a talk unto itself. I'll be happy to explain in more detail how we do parallel mesh generation, and I can point you to the reference, but we developed the algorithm for that 15 years ago for parallel mesh generation. Very quickly, underlying, the key thing is how do you parallelize an operation when you don't want to know what you're going to parallelize, because you want to parallelize ultimately on a mesh. We take the geometric model and start with an octree and mesh control information, dynamically drive the octree, keep that distributed in parallel as the mesh is generated in parallel.